All right, this is a video of Introduction to Complex Numbers, the Desmos activity. The warm-up says to solve by completing the square. So first thing you're going to do is subtract 12 from both sides. And then you want to take 8 divided by 2 is 4. And square 4, 16. Add 16 to both sides. And then square or factor the left. And take the square root of both sides. Have a negative under the radical, then you need to pull an I out. So x plus 4 equal, this should be plus or minus here. So pull an I out, and then you get plus or minus I square root of 4. And on the next step, I'm going to subtract 4 and do the square root of 4 over here. So subtract 4 from both sides and then do the square root of 4. So negative 4 plus or minus 2i. In the next few slides, you'll see if you have a square root of a negative number, it's going to be square root of negative 1 times the square root of 4. And the square root of negative 1 is I. So we'll look at that on the next few slides. So what do you notice here is that then when there's two solutions, there's two x-intercepts. One solution, one intercept, x-intercept, and no real solutions here. No x-intercept. So example 1, if there are two x-intercepts, there's two real solutions. Example 2, there is one x-intercept, one real, say one repeated real solution. Example 3. If there are no x-intercepts, there are going to be two complex solutions there. Or one repeated complex solution, or one repeated imaginary solution. So another way we can do that is find the discriminant. So b squared there it goes. So we can say if b squared minus 4ac is positive, and the second condition, if b squared minus 4ac is 0, there's one real solution. And the last condition, if b squared minus 4ac is negative, and there are no real solutions. There's going to be two complex solutions. We go back up here. Our b value is 8, a is 1, c is 7. So example 1, 8 squared minus 4 times 1 times 7 equals 64 minus 28, which is equal to 36. So the the discriminant is positive, there's two real solutions. Example 2. Example 2, A is 1, B is 8, C is 16. So I have 8 squared minus 4 times 1 times 16 is 64 minus 64 equals 0. So we have one real repeated solution. The vertex is on the x-axis. Example 1, there's two x-intercepts because the discriminant is positive. And then example 3, B is 8 again, A is 1, C is 20. So you got 8 squared minus 4 times 1 times 20 equals 64 minus 80. So negative 16. There's no real solutions there. But the most important thing about this slide is this. 2 x-intercepts, 2 real solutions, 1 x-intercept, 1 real solution. No x-intercepts, then no real solutions. Slide 3 is just an information slide. You can do warm-up notes and practice. Slide 4, another information slide. The square root of a negative number has no defined value as either a rational or irrational number, making it impossible to determine real zeros of a function like a warm-up h of x squared equal x squared plus 8x plus 20. Because we want to be able to determine the zeros of a quadratic function like that, Leonhard Euler proposed that the new number I is equal to the square root of negative 1 to be included in what came to be known as the complex number system. So if I is equal to negative 1, then I squared, I is equal to the square root of negative 1, then I squared is equal to negative 1. And then on 5, so rewrite the square root of 2, or square root of negative 2, would be a square root negative 1 times square root of 2 which equals I square root of 2. And the square root of negative 4 is square root negative 1. You don't have to do this every time, but I'll just do it for emphasis. That the square root of negative 1 is equal to I. So I square root 4, which is equal to 2I. And the last one, I'm going to skip this step here. Square root of negative 1 times the square root of 10. So it's just going to be negative Put your I out, I square root negative I square root of 10. So the first one, I square root of 2, second one, 2i, last one, negative I square root of 10. And then we can also simplify imaginary numbers. So 4 times 3i would be 12i. We use the equation under it. Looks neater when I do it that way. And then 3i times 3i is 9i squared. And wherever there's an I squared, you can put a negative 1. And here, this actually means this. So square root of 2 times the square root of 2 is 2. So 2i squared. So 2 times negative 1. So wherever there's I squared, I put a negative 1. 2 times negative 1 is negative 2. So the first one's 12i, second one negative 9, third one negative 2. Complex numbers of the form a plus bi, where a and b are real numbers, and I is equal to negative square root of negative 1 are called complex numbers. 4 plus 5i is an example. Numbers like 3i and 2i are pure imaginary numbers because they're made up of only an imaginary term. So how can you determine if a quadratic function has complex zeros from the graph? The graph has no x-intercepts. Then the function Alright, so this has no x-intercept, so it's going to have complex zeros. If I solve this equation, then negative x squared is equal to 2, and then divide both sides by negative 1. So x squared equal negative 2. Then take the square root of both sides. X equal plus or minus square root of negative 2. And then pulling your I out of the radical. X equal I square root of 2. two solutions, I square root of 2 and negative I square root of 2. Determine complex 0 is here, so I can see that this parabola has no x-intercepts. Solving this equation, x plus 2 squared, and then subtracting 3 from both sides. And then take the square root. So plus or minus square root of negative 3. And then subtract 2 and pull the I out of the radical. Subtract 2. And pull the I out of the radical. Negative 2 plus or minus I root 3. And the extra practice, pull your I out. I square root of 7. Pull your I out here, negative I square root of 29. One I out, I square root 25. But we know what the square root of 25 is, it's 5. So you get 5i for that one. And the square root of negative 1 is just I. Wherever there's an I squared, plug in a negative 1. 2 times negative 1 equal negative 2. And square this whole thing. 4i squared equals 4 times negative 1, negative 4. I plus I, because this combining like terms, 2i. 6 times 7i, 42i. Negative 5 times negative 1. It's 5. And I cubed, you can change that to I squared times I. And substituting a negative 1 for I squared, you get negative I. All right, and then 12. Determine the non-real zeros of each quadratic by setting it equal to 0 and solving. Rewrite the zeros using the number I. So 0 equals x squared plus 1. Subtracting 1 from both sides. And negative 1 equal x squared. Take the square root So plus or minus, whoops. Get the equation under. And then get plus or minus I. And then here's 0 equal x squared plus 9. Back 9 from both sides. Square root of both sides. And square root of 9 is 3. And pulling your I out, so 3i. So both of these should get pure imaginary solutions. If you graph these, still no x-intercepts. That's it for that activity.